Good morning. Welcome to Krishna's classroom. We begin another episode on Riemann integration. We have so far completed 3 episodes, and last time we ended with defining integrability in the sense of Riemann. And we were very restrictive in the sense that we assumed the following. We assumed that you have an interval AB with A infinity. So it's a compact interval that we are looking at, on which we define a function f from R, and we assumed that f is greater than or equal to 0. Now this is an assumption that we could get rid of. This is where we started. And for this function, we further assume that this is bounded, therefore there exists an M such that so these are the 3 assumptions that you have on this function, of which f greater than or equal to 0 is something that we can get rid of. But I had chosen to keep it in order to tell a few facts about doing mathematics and induce rather less confusion at the stage of certain constructions. But we will soon get rid of that. So what we have now is a function of this kind, and we defined f is integrable on AB if the lower integral is equal to the upper integral. Just recall the definitions of lower integral and upper integral. And we also pointed out that with these assumptions, it is not possible to assure that the lower integral the equality of the lower integral with the upper integral. Although we can assure that the lower integral exists, the upper integral exists, they may be different. And we also looked at the famous Dirichlet function, which has the property that the lower integral and the upper integral differ in that particular case. So this is something, although all these conditions are satisfied, so this is something which we cannot assure. Now, having got this, we explore some of the properties of a Riemann integrable function. So, a function f satisfying these properties and Riemann integrable, that is, the equality of the lower integral and the upper integral is valid. Then we see what kind of properties this integral has. For instance, some properties that we find, if f and g are such that f and g are bounded by m1 and m2 respectively and are Riemann integrable, then f plus g is Riemann integrable, comma, CF is Riemann integrable for C positive or C non-negative. Further, integral A to B f plus g dx is equal to integral A to B f dx plus integral A to B dx. So also integral A to B CF C times now these are straightforward to explore and prove, but one should prove this. And of course, the best way to learn mathematics is by doing it. So you put your hand on these kind of things and explore a proof, learn how to write a proof. Okay. So having proved this, we now take up the task that we promised, that we will get rid of this artificial condition that f is greater than or equal to. So let us explore this problem. Now we have actually we wanted to look at any f as generously defined an f as possible on the interval AB, for which Riemann integration can be defined. So we assume the following. Assume f is bounded on AB. That is, to have small m and capital M such that this is one assumption that we make. So we assume that f is a bounded function. And we are no more going to assume that f is non-negative. Now see what can be done for this, because we explored Riemann integration for functions which are non-negative. So if somehow or other you could bring it to that language, that means although we are not assuming f is not necessarily non-negative, then what we have to do is we try to express it in terms of what is called a non-negative functions, if that is possible. So that's what we are going to explore next. So is it possible to express f as a sum of non-negative bounded functions? If that is possible, then you can use this part of the theorem. And if the two parts that you have got are both f and g are non-negative, and their sum is, or the first part and the second part are non-negative, and they add up to the function that you started with, then if they are Riemann integrable, then one can write this and define Riemann integral of the sum as the sum of the Riemann integrals. That way we will be extending to non-negative functions. So let us see how we can do it. Maybe a little bit of say graph of the function would help you to think about it. Okay. So we take up an interval. Now suppose this is the graph of the function. So this is y equal to f. Now what we want to do is we want to express this, if possible, as a sum of two non-negative functions. So how do we do that? First of all, we extract out a non-negative function from this, which is partly equal to f on the interval a. That means wherever the function is already non-negative, we define the new function as itself. So we designate that function. So we define a formula f plus of x defined as maximum of fx and 0 on the interval it's pretty clear. What is it? You take this point. There fx is already positive. And what is the maximum of fx and 0? It is fx itself. Whereas if you take this point, then fx is negative here, and the maximum of 0 and fx in that case is going to be 0. So your function that you choose as f plus is the following. Wherever the function is positive, f plus x is equal to fx. Wherever it is negative, set it as equal to 0. Similarly, you define f minus x to be equal to, and here we have to do little what? What we do is we completely reflect this function on the x-axis. That means we look at the function minus fx. What is minus fx? Minus fx will be something like this. It's reflection of this. So you have, see, this is the reflection of the function. I mean, may not be very correct in the picture. This is the reflection of the function f on this. Now what one does is f minus x you define as maximum of x belonging to AB of minus fx and 0. What does it mean? To take a point here x, then you see that fx is positive, therefore minus fx is negative. So at this point we set the function f minus to be equal to 0. So let us draw the graph of it using some color display. So what you have is, here you take this as 0, and then on this part where f is already negative, Therefore, minus fx is already positive. Therefore, the maximum of fx minus fx and 0 is minus fx. So, you take this portion and then on this part it is going to be equal to 0 again by similar argument.
The two functions displayed here are f plus and f minus, which are non-negative functions.
Now, how do you get back your f from it? You can easily see that fx is equal to
Figure 4 gives a consolidated picture from which one can see that fx is equal to f plus x minus f minus x.
So we have successfully written the function f as the difference of two non-negative functions. Now the question that you ask is f plus Riemann integrable? Is f minus Riemann integrable? If both of them are Riemann integrable, then you are done. You can define the Riemann integral of f as the difference of the Riemann integrals of these two functions. So this is what one does. So is bounded or f plus f bounded and greater than or equal to 0? This is the question. The answer is so again you need a one-line proof for that. Then of course the second part is now what we do is are these functions Riemann integrable? This is something which you cannot be sure of. But what you can say is that if both f plus and f minus are Riemann integrable, then you can compute the integral of these functions. So we assume that this is not automatically assured. In fact, they may you can think of an example. Quite easy to construct an example. What do you do? See, we already have the Dirichlet function. And the Dirichlet function was f equal to 1. See, we were considering the interval 0, 1. And the Dirichlet function was f equal to 1 at all irrational points and f equal to 0 at all rational points on the interval 0 to 1. That is a function. So we have 1 at x belonging to 0, 1 intersection Q complement and f equal to 0 at x belonging to 0, 1 and intersection the rational points. This was the Dirichlet function that we considered. Now what we do is we change this. We change this and write this as minus 1. Okay? Change this and write this as minus 1. Okay? Now you see that this is a function of this type. The one that we have looked at, it is bounded on the interval 0, 1. But not non-negative function. So what one does, we try to construct both f plus and f minus for this function. I leave it as an exercise for you, construct f minus for this function. Then you see that both f plus and f minus are Dirichlet functions, probably with a change in the value, but both non-negative, and they are not Riemann integrable. Therefore, their sum also, the sum of their integrals cannot be. So this is the problem. So it is not automatically true that a function which is bounded on the interval a to b has both f plus and f minus Riemann integrability. That is why we have put here, asked the question, are these functions Riemann integrable? So now we put that as a condition. We put that as a condition and write if f plus and f minus are Riemann integrable, then write define integral a to b, the Riemann integral of f. So that is the definition of the Riemann integral. So this is subject to the condition that both f plus and f minus are Riemann integrals, and this is the definition. That is one way of getting there. In fact, this is not necessary to resort to this method at all. One can directly assume a function f just bounded, and for that go through the entire exercise that we did earlier. But I decided to go along this route to drive home certain points. First of all, I don't want you to confuse with the definition of the step functions in those cases, in the general case. And also, I wanted to show you that if a general problem cannot be addressed, what one does is you go to a related problem where you are more comfortable, and then try to reduce the general problem to the related problem. If that can be done, then you are through. So here what we have done is, we were interested in the solving whether f is Riemann integrable. We resolved that problem for non-negative bounded functions. Now we resorted to writing f as a difference of two non-negative functions, and if these two components are Riemann integrable, then you say the function f is Riemann integral. This is our, and that's how we extended the whole thing. However, one can extend this without doing that. I just make a remark here.